Hey, welcome to The Explainer. Today, we're going to talk about something we all use every single day, but maybe don't think about too much: measurement. And no, this isn't going to be some dry, boring math lesson. We're talking about decoding the language of reality itself. It's about the fundamental rules we use to describe, well, everything, from a tiny little atom all the way up to the entire universe.
So, here's the plan for today. First up, we'll ask, what even is a unit? Then we'll meet the 7 fundamental building blocks of all measurement. After that, we're going to see how to mix and match them, check out the tools of the trade for physicists, and finally, we'll put it all into practice. All right, section 1. What is a unit? Or maybe a better way to put it is, why is a number all by its lonesome completely useless?
Okay, so picture this. I tell you, hey, the mass of this thing is 60. What does that even mean? Is that heavy? Is it light? Are we talking 60 grams, like a tennis ball, or 60 kilograms, like a person? Maybe 60 pounds? See, without that little bit of extra info, the number 60 is, well, it's totally meaningless.
And this is how we fix it. A real, actual measurement needs 3 things. You've got the quantity, which is just what you're measuring, in this case, mass. Then you have the magnitude, that's your number, 60. And then the real MVP, the thing that gives it all context, the unit. Here, it's kilograms. You need all 3 of those pieces: quantity, magnitude, and unit, or you're not really saying anything at all. All right, let's move on. The 7 base units. Now this is where things get really cool. You might think we need a zillion different units for all the things we can measure in the universe, right? But it turns out we can describe pretty much everything with just a handful of them. These are the absolute building blocks of measurement.
And here they are, the magnificent 7. You've got the ones you know and love: length, measured in meters; mass, in kilograms; and time, in seconds. Then we get a bit more specialized: electric current, that's amps; temperature, which is Kelvin; and for all you chemists, the amount of substance, which is the mole. Oh, and the last one, luminous intensity, in candelas, which is basically a measure of brightness. That's it, just 7. Think of them like the primary colors of the universe. Every other measurement you can think of is just some combination of these. Okay, so if those 7 are our basic ingredients, what happens when we start cooking with them? This brings us to our next section: building with derived units. We're going to start making some recipes.
So let's make our first derived unit: velocity. I mean, what is velocity when you break it down? It's just how much distance you cover in a certain amount of time, right? So the recipe is super simple. It's just length divided by time. And what does that give us? Well, meters per second. It makes perfect sense.
Okay, let's try a slightly spicier recipe. Let's talk about force, a push or a pull. The recipe for this one uses 3 of our base ingredients. It's mass times length, all divided by time, or time squared. This gives us the unit kilograms meters per second squared. Now that's a mouthful, right? So physicists gave it a nickname, the Newton. But don't let the fancy name fool you. Underneath, it's just mass, length, and time all mixed together. So we have our basic building blocks, and we know how to combine them. Now we need the tools to handle it all, which brings us to the physicist's toolkit. These are the essentials for actually speaking the language of science. So here's a good question. Do scientists all speak the same language? And the answer is kinda yes and no. We're all describing the same universe, for sure. But historically, different groups have used different, well, let's call them dialects. It's like saying hello, hola, or bonjour. It all means the same thing. You just have to know which system you're using.
Let's look at the 3 most common systems. There's the FPS system, which you might know as the imperial system: feet, pounds, seconds. Then there's CGS, which stands for centimeter, gram, second. But the big one, the one that's the gold standard for science all around the world, is MKS, also known as the SI system. That's meter, kilogram, second. And you know what's kind of funny? Look at the time row. Pretty much everyone agreed that the second was the way to go.
The next tool in our kit is for dealing with crazy big and crazy small numbers. I mean, nobody wants to sit there and write out 9 zeros after a number, right? It's just asking for a mistake. So instead, we use scientific notation. It's a super clean way to just tuck all those zeros away. You write the main part of the number and then just use a power of 10 to say how big or small it is. So much easier. Now, scientific notation is awesome, but you know what? There's an even faster way to do this for common sizes, and that is prefixes. So let's say you've got 1,000 meters.
You don't say 1,000 meters, you just say 1 kilometer. That little K is just a shorthand, a code that means 1,000 of whatever comes next. Easy, right?
And it works the other way too. Let's say you have a tiny amount, like 1,000th of a gram.
We just slap on the prefix milli and call it 1 milligram. You see these everywhere. Giga for billion, mega for million, micro for millionth, nano for billionth. They're just super convenient shortcuts so we don't have to say all those zeros.
Okay, we've got our base units, we know how to derive new ones, and we have our toolkit for handling different systems and sizes. Time to put it all together and solve a real-world problem.
Let's say you're driving at 100 miles per hour, and you need to know what that is in kilometers per hour. First step, you need the conversion factor. You look it up. 1 mile is about 1.6093 kilometers. Simple enough. Step 2, you set up your math. You take your 100 miles per hour and you multiply it by a clever fraction, 1.6093 kilometers times over 1 mile. Now step 3, this is the really cool part. Because you have miles on the top on one side and miles on the bottom of the fraction, they just cancel each other out. All you're left with is kilometers on top and hours on the bottom, which is exactly what we want. Last step, you just crunch the numbers and bam, 160.93 kilometers per hour.
And really, that's the whole point of all this. It's what allows for universal scientific communication. It doesn't matter if one person is working in feet and another is working in meters. As long as you know how to convert, as long as you understand how these units are built, everybody can be on the same page. We can all speak the same language.
So, I'll leave you with a little puzzle to chew on. You probably have a device with a terabyte hard drive. Now, we know that tera is just a prefix, right? It just means a trillion. But what about the byte itself? That's a derived unit, just like the Newton was. So my question to you is, which of those 7 fundamental units we talked about, length, mass, time, current, and so on, which of those do you think you need to build a byte, a unit of pure information? It's a pretty wild thought, connecting the physical world we just described to the digital one we live in. Think about it.